Hi there, and I would like to start my lecture by giving a very interesting example that occurred to me and my kids last night when we were at the swimming pool, and it was a lesson we all learned about wave impedance. So basically my young one discovered together with me that if you say something and the other person saying something is on top in air and the person who is trying to listen is in water, you can quite easily listen what the person is saying when the person is saying it on air, but it doesn't work out the vice versa. So that when the person is actually saying something underwater and you try to hear it out when the person listening is actually on air, it doesn't work like that. And I instantly started thinking about wave impedance. It's a very interesting parameter. And I was thinking about total internal reflection that we have also discovered on this course. And we have actually learned that it can be used to make optical instruments and components. And for example, it's being used in prisms and so forth. So basically, we all know that the speed of sound in air is roughly 300 meters per second. And of course, we also know on 101 from solid state physics that if you have a more dense material, then the speed of sound usually is higher in that material. And that is also the case of water. I do not recall how much it is, but for sure it will be around 1,000 meters per second or something like that. In any case, the take-home message is that the speed of sound in water is higher, and this then makes the reflection process and refraction processes to behave exactly equal in similar way as we have learned in the optics. And then because we can look at the we could calculate the Fresnel coefficients for sound similarly well as we can do for light, and we could then learn that in fact the sound waves can go through a total internal reflection at the air-water interface, and because of that the person does not anymore hear what the person is saying underwater. But the other way around works perfectly fine, and we were quite intrigued of this phenomena last night at the swimming pool. And you should take your friend and try it out the next time you're somewhere in aqueous environments. And because I think it's a really cool demonstration of wave impedance and how wave impedance, so basically the change in the refractive indices, change in the speed of wave propagating in these two different media of interest affects the what happens. So I felt that this is very cool, and it's very nicely generalizing the topics that we have discovered into a different topic that now we're looking at the sound waves. But then, sorry of branching out this 3-minute starting point, but I felt that this is something I must convey you, my patient listeners, because I thought that this is super cool stuff. And now the actual main point, what I will be speaking to you about during this lecture, I will be speaking roughly what's an eyepiece and why they are being used in optical instrumentation. So basically, eyepiece, also known as an ocular lens, is a component that is used in many optical instruments. And one instrument that the first comes to my mind is an optical microscope that will be discussed in the next lecture. And what is the function of an eyepiece? Well, first of all, it can change the magnification of our system. But basically, why they are being used in practice is that they help reducing the optical aberrations of our instruments that are formed using lenses. And that also, in addition to this, using eyepieces also make instruments more modular, so that you can, for example, change the other components in your system without affecting the performance of your component that much. But I will speak more about this on the upcoming lecture when we will be speaking about microscopes. And then, of course, recalling how the transverse magnification of two lens system goes. If you have two lenses, then you can increase the transverse magnification by just having the second lens, and this is what the eyepiece, also known as the ocular, effectively is. But now let's go to my one slider lecture about the ocular, and how I will now go through it quickly. So basically, optical instrumentation that uses human eyes directly for making measurements. Like there, we often have eyepieces. And then in the kind of simplest possible scenario we can imagine, when we have an optical instrument, for example, an optical microscope, we have two lenses. And that has been shown in the figure. So we have objective lens, that is the first lens closest to the object you want to image. And then we have this ocular afterwards that is helping for the image formation process. And this configuration, like, is a very conventional, and basically what it helps us is that we can then use an objective lens that forms an image, and then we can get a given transverse magnification, and after that we can use the eyepiece to get even further magnification, and then we can use the eyepiece also to reduce the aberrations associated with the image formation process of an objective. So this is actually quite complicated, so that when you would really want to design things, because how things would go is that you would have some aberrations present in the intermediate image in here, and then the eyepiece intentionally would be designed to counteract those aberrations, so that in the end, when you would have the final image, there would be a minimization of aberrations. But this is actually quite complicated because you have two lenses and image formation processes that you need to take into account on the designing process. But nevertheless, like in the simplest possible scenario we can imagine, we have the objective lens, and this is the one that is closest to the object that is being described with the SO1 and YO1 parameters. YO1, of course, being the distance of my object point from the optical axis. And now this objective lens forms an intermediate image between the lenses, and they are being described with the SI1 and YI1 parameters. And then this second lens, known as the ocular lens or eyepiece, forms the final image, or actually it doesn't form an image, but rather it forms an image into the infinity. And then when we would place an eye here, then we would be forming an image into the retina. And the nice thing of this, why on earth we do not want to form another image, is that if you recall, the eye is in a relaxed state when we are looking at objects that are at the infinity. So when the objects are far away. So if we want to use the microscope to inspect something for a longer duration, we want to be able to use our eyes that are in a relaxed state, so that we do not need to squint them all the time, but rather we can just be relaxed and in a comfortable inspection mode. And this is what the IP does essentially, that it's transforming an intermediate image into an image that will be formed at infinitely far, so that when we place the eye at the right location, we can actually form an images, and then we're actually able to look what happens here at the kind of imaging plane of my objective lens. And this is in a nutshell what is the kind of function of our eyepiece and how it behaves. And let me repeat like a kind of main benefits why we use ocular lenses. Well, first of all, we can change the transverse magnification by adding a lens. The second reason is that if we use our eye to inspect, then we can form an image that would be formed at infinity, so that the eye can be relaxed when we are inspecting things. Then the addition that we get is that we have more modular way of making my microscope, for example, or another optical instrumentation. So that I can then change more easily my objective lens into a different objective lens that would, for example, have a different transverse magnification. And as long as I just change the objective length, and I can still form an intermediate image at the same plane as before, then the eyepiece works as before, and I do not need to change anything else in my configuration. So basically, it allows me to make more modular microscope or another component, and that modularity just means that I can change objectives more easily. So for example, I could use a rotating microscope lens of the objective lens turret here, and I could really change the actual magnification of my microscope quite easily in a few seconds by just rotating the microscope objective lenses in my microscope frame. And this is being made possible by the fact that I actually have two lenses here, so that the objective lenses, as long as they are being designed such that they form images in a given intermediate plane, then we do not need to adjust how the eyepiece works, and we do not need to adjust where the eye is in order to make the inspection. And the final point, and this is not mentioned much in the textbooks, but we know that in practice, when you buy objective lenses and when you have eyepieces, depending on the manufacturer, the aberration corrections are done slightly differently, so that in fact the companies are being balancing out that some of the aberrations are being corrected at the objective lenses and some of them are being corrected at the eyepieces. So that if you do the mistake of buying different lenses from different vendors, so then you might be in trouble because they are not like really intercompatible, because it might be that then the eyepiece will be correcting for aberrations that are not like placed in there anymore with the objective lens you have bought from a different vendor. So please be warned of that kind of possibilities also, and of the fact that the kind of aberrations of your total lens system now, because you have two lenses, you can actually do tricks by utilizing both of them and doing lens bending, lens designing to make it behave as you wish the system to behave. So this was my prelude motivation to the next one, the next lecture that I will be using to teach you about microscopes. But I hope you got the main points that in fact microscope is not an optical instrument that is as simple that it would only consist of a single lens. So it's not a magnifying glass in that sense, but rather something slightly more complicated. But I thank you for your time and patience, and please join me shortly on my lecture regarding microscopes. Thanks. Bye.